So it is a great pleasure to announce Zhilin Luo, who will be speaking about the algebraicity of BunG and a little bit on the automorphic interpretation of BunG as well.
Okay, so I'd like to thank Aaron and Nick for the invitation. Okay, so today I'm gonna talk about the algebraicity of BG and the BunG. So here, let's assume F is projective. Maybe let's assume it's very close. And we will recall an automorphic interpretation. So there was a step of vector bundles of rank n over X, which is integrated. Okay, so first let's briefly recall the definition of pre-stacks and the stacks of the last problem. So let's recall the setup of the last time. Let us fix K, which is the commutative ring. And we let's see out the category of K commutative, K algebras. And the definition and algebraicity over K, is defined to be a representable function. From this characteristic set. Okay. So in particular, we can freely identify this category of the opposite category of all outline schemes using the Weil lemma. Okay, so let's recall the last time we introduced the concept of pre-stack. So this is defined to be the functors to get rid of all group lines. So roughly speaking, for any such pre-step, and any K algebra A, you get a group line. In other words, all the arrows are invertible. And for any motion from algebra A to B, okay, we get a corresponding function. And so that it satisfies some compatibility. So first, there should be a natural isomorphism of the body of A from the identity factor of XA, okay, to X on identity. And the second, every time we have a chain of morphisms, okay, from A to B and to C and G. There should be a natural isomorphism, okay. Here. From the function x G composed with F. So that it satisfies abilities. Okay, so for instance, the division of and second, the isomorphism eta A okay should have compatibility with this metric transformation. Okay, so usually in the literature, such a pre-stack will also be called a pseudo function. Okay. So basically, let me write here. A stack is just a pre-stack with some fluid drop. So whenever we say we are going to glue something, of course, we need to equip some topology, okay, or category. So for instance, throughout our talk, we will always work with the tail topology, for instance. Okay, so basically, open cover is something like a fraction of the terminals. So here, both UI and U are affine. Okay. Yeah, affine schemes, okay. And then you assume that I here is a finite element. And you have fully fixed subject. Okay. Cool. Of course, here you can switch the tail morphisms to other morphisms. Okay, then you will get different topology. Okay. So let's recall. Okay, so we have seen the definition of stacks last time. Okay, so basically a pre-stack X. Okay, it's called a stack. If it satisfies the following two gluing property, okay. So first, it can glue morphisms. So then the definition of it. So a pre-stack is called a stack. If for any open covering, we have the following gluing property. First, we can do morphisms. Let's first do an object. Okay. So basically, if we have a collection of objects on each smaller subset or in smaller open cover, with some isomorphisms of and satisfy the co-cycle condition. Yeah, okay, with respect to JK, okay, composed with JK on the triplet intersection is equal to okay. Then there must exist an object, right? Inside X2, okay, is such that this has more. Such that I have to compose this ER. Okay. Okay, so roughly speaking, it just says that if we have a collection of objects on some smaller oversets, okay, and if they satisfy the co-cycle condition, then we can glue them together, okay, and get an object within the big overset. And the second, we can glue morphic. So when any x1, okay, inside object of x0. The following pre-shape, okay, which any open subset we send to its restriction. It's really a sheet. Okay. Okay. So equivalently, equivalently, it just says that for any x in the line, okay, you say object. And if we have a collection of isomorphisms of a restrict to some smaller subset, okay. Such that things go inside with each other on overlap. And there exists a unique global isomorphism such that restrict to each value. Okay. Okay. So usually the literature, special collection of objects here, okay, it's called a descent datum. For this curve. And if this property holds, okay, if we can really glue the objects, usually we call it descent datum, it's effective. Okay.
So for all of you who were worried that we were being too wishy-washy, that is the full definition of a stack.
Yeah, so,
yeah. That written out in glorious detail.
yeah, so indeed, the idea is straightforward. Okay, basically, we can not only do the motions, we can also do the sheet or do the object. So any question?
I guess just as a comment to like link it to the definition, I said that some morphism of groupoids is an equivalence.
Yeah.
So your condition 1 is saying that that morphism is essentially surjective, and condition 2 is saying that it's fully faithful.
Yes, okay, it's a very good point. So let's recall that last time Justin write a two limit diagram to interpret these two conditions. Okay, so as an exercise, okay. You need to check that definition here. Okay, really go inside the two limit diagram.
Sorry, I gave an unsolicited hint.
Yeah. So you basically need to write down the definition and then check one by line. Okay, then you will figure out. Anyway. Any other question? Okay, let's continue. Okay. Okay, so let's see some example. So let's introduce the main object that we want to study today. So for X scale, let's consider the following precept, which is known as BunG n X, which sends any affine scheme as to the group point. So BunG S X S X S. Okay, so this is the group point of vector bundles of rank n on S. And the morphisms are just automorphisms of vector bundles. Okay. So in general, so in general, suppose we have two affine schemes, okay, and we have two vector bundles, V1 over X. And V2. X. Then a morphism between them is just given by a pair. It's given by a morphism from S1 together with the isomorphism of two vectors. So let's see this identity as trans P, then you take the full vector. What is okay. Now let's check that indeed this is a step. Okay. Okay, let's see. Okay, so first let's check the. So okay, let's show that final F is that. So of course there are two parts. Okay, so first we need to show that indeed it's a three-step. So in other words, we need to show that this functor has some computabilities, okay, natural computabilities. So for instance, if we have a Morphin bracket form, let's do okay. Then the corresponding functor actually is given by the fullback of vector function. But you know that the pullback of vector bundles behave well under composition and all kinds of compatibilities. And therefore, indeed, it is a preset. And then we need to show the gluing condition. So first, let's show the gluing object property. Okay, so let's see. So let's translate everything line by line, okay, to our setting. So what's the meaning of gluing objects here? Okay, so basically it says that suppose we have a collection of vector bundles, okay, on a glue cover. Okay, so let's open the cover. And we have a collection of vector bundles of rank n, okay, vi on ui. Okay. And if there are isomorphisms, okay, alpha I, okay, the transition morphisms, okay, from vi speak to the second, it's dj, okay, to the ij. And if the isomorphisms satisfy the co-cycle condition, alpha ij composed with alpha jk, okay, is equal to alpha I clear. Then indeed we can do these vector bundles to the whole vector bundle on U. Okay, but this is exactly what we have seen, for instance, in classical topology. Exactly what we have seen in differential multiplication.
So clarify we're using the heuristic topology here.
I know this is a tall topology, so you are implicitly to prove that those things glue, you'll definitely be using the descent, right? The tall descent, yeah.
Yes.
I think a tall descent for quasi-coherent sheaves or a tall descent for affine morphisms, both. One's a special case of the other, but
So here we use the protocol. So indeed we can glue them to be a global vector bundle on U, okay? Now let's see the gluing of morphisms, okay? So basically the gluing of morphisms just says that if we have a morphism between, if we have two vector bundles, okay, and then we have morphisms between each small disk, okay, and if they coincide on the intersection, then you can glue them together to a homomorphism between two vector bundles, okay, but that's basically just a definition. Okay. So from here we deduce that indeed bound and X, okay, is a static. Any question? Okay. Let's continue. Okay, so here I want to make a remark. Okay, so for vector bundles, in general, the audience just said that indeed we need to pay attention to the topology we are using here. So for vector bundles, we are lucky. It turns out that we have the following statement. for vector bundles, rank n. Actually, you can show that the Zariski local triviality is equal to the general triviality. And it's equal to the PDF. Okay. So basically, as an exercise, I mean, if you have a PDF local trivial vector bundle, it means that you have a flat and a finitely presented module. And here it means that you want to projecting module. And then run a basic exercise from cognitive algebra, you can show that any finite projecting module is actually locally in Zariski. In particular, when x is equal to a, we usually just write find x, x, and okay. Okay, so any question? Okay, let's continue. Okay, so I believe that you have heard that indeed we can always identify vector bundle is a GIN bundle. So in general, for any algebraic group G, okay, we can introduce the notion of G bundle. Or in some literature, it's called G tensors. Okay. So let's introduce the definition of it. Let's see. So let's assume G and alpha is smooth group speed. Okay. Or let's assume it's finite time. Okay. Over Q. Okay, so for example, most of the time we will just want to use those inductive or even semi-simple group. So for instance, you can look at the general linear group or the symplectic group or orthogonal group. Or maybe special group. Okay. And we let X just unique. So as you can imagine, the definition of G bundle over X, I mean, it's very straightforward. Basically, it just means that locally we have a triple G bundle. So a G bundle on X is a sheet on the tail side. Okay. And with a schematic loss. So from P to okay, such that locally is automorphic to Weil plus G for some tail cover. Okay. So indeed, it just means that okay, locally it is a form like Weil plus G. Okay.
It doesn't do-
Yes, okay, so let me add.
Insist that those isomorphisms are G equivariant.
Okay, so indeed, when you say G bundle or G tensor, here usually we require that there's an action. There's action map. So when we say that it is group action, it means that for any open, there is G. Do this shape of test, okay, then this is a set. This is really this what should I say that? And this is a group action of it. Okay.
It's true though, right? You're saying. Wait, for any U. It's locally a G tensor, right? But
It's locally a group. Yeah.
Oh, so you want to exist, so you.
it's there exists the cover.
Yeah, not for all couplings, right? They're.
Yeah.
I mean, if you cover X with itself, unless it has a section, it won't be.
Yes, yes. So yes, so here we require there's a GI. Yes. Any other question? Okay. 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 But here, I mean, basically, we assume G is smooth, okay. Again, the local triviality of G bundles in intelligent technology, okay, actually, it's the same as the local triviality in FTPF. If G is not smooth, usually one works with FTPF topology. Okay, moreover, so here we notice that because we assume our group G is affine, then actually using the FP QCD set for affine motions, we can show that indeed P actually is represented by affine speed over F. So using the QCD set for affine motions, indeed you can show that P is represented by affine speed of F.
So this is in marked contrast to if it's not happening, it's like the curve, which
Yeah.
was Justin's horrifying example from last time, right?
Yeah, so the line. So in the last time we had heard just this talk that it's not affine. Yeah, it can happen that P might not be represented.
Also, as mea culpa in the notes for the first talk, I also made exactly the mistake Justin warned us about and misdefined what a family of curves is. It works for genus 2 or higher for technical reasons, but not for genus 1. So you need to make the space, algebraic spaces.
So I guess in the general case, you don't want to assume the pi is schematic, right? Because that's exactly like it'll exactly be affine if G is affine, and in general, it doesn't need to be schematic at all.
I see.
Yeah,
I
I
see.
think no condition.
I see. Okay, any other question? Okay,
Wait, sorry, in the definition, it's that such that there exists U to X, right? Like, is that what you changed? Like, is that what-
it's u to x, yes, u to x.
or like in the line, oh, okay. Wait, so is that the definition of a G bundle, like such that there exists? Just all that above and then there exists covered U to I such that
Yes.
G U I. Thank you.
Additional structure, which is the group action. That you didn't mention the first time. Right?
Yes, yes. Maybe I should erase. Thank you. Okay. Any other question? Let's continue.
Sorry, my confusion, is it shape defined on app or app of X?
You mean shift defined over?
Like, is that nice, is that?
It's a good point. In the literature, usually when people define the G bundle, a G bundle over X is defined to be a sheaf on schemes over X. But because in our setting, actually, we start everything from affine tensor, so I want to just define it this way.
Is it like the big and the small side you're asking?
There again,
I think the.
So you're talking about the big site of equipped with the map X. That's the same thing as giving.
That is a good question though, yeah, whether it's all schemes or just the atomic. Is the one thing.
I'm so sorry, one last question. Is the part that PUI is a GUI torso at the set, is that part of the condition?
it's definitely part of the condition.
Okay.
Okay, any other question? Okay, let's continue. So, similar as the situation of vector bundles, okay, we can introduce a modular stack of G bundles on X. Okay. Basically, it just sends an alpha screen to the group part. Of G bundles. Okay. So here, we notice that over the same base of the if we have two G bundles, then any G covariant morphisms between them must be an isomorphism. Okay, so basically we have to a local trivialization, okay, and look at the G covariant maps between two triple bundles, you will see immediately that it must be isomorphic. And in general, similar to the situation of vector bundles, so if we have two G bundles over two different bases, yeah, morphism between them is basically just a commutative diagram. Okay, so G covariant commutative diagram. And moreover, you can show that indeed this diagram must be partition. Okay, it's an exercise. So basically, because by definition, I mean, let's see. So P2, okay, you have a method map if you want it. And by the discussion here, it must be isomorphic. Therefore, this diagram must be partition. Okay. Let's see.
So actually, we're nearing break time.
Really?
We have like, we could either, go depending on your preference. So if we.
So I think maybe just 1-2 minutes left for the last.
Okay,
Yeah.
sure.
Okay, so, okay, indeed, you can show that BunG X of the indeed is back, okay. We can include the G bundles and the motions, okay. And in particular, when X, it's just that K, okay. We can know it as BG, okay. We can maybe write point. This is a classified step of G bundles, okay. And finally, let's make a remark that indeed vector bundles of rank n, okay, can be identified with n bundles. So if we start from the Zhilin bundle here, okay, we can send it to the corresponding social bundle. And then conversely, if we have a vector bundles of rank n, okay, we can send it to the the isomorphism shifts, okay, from the trigger bundle to D, okay. And you can show that indeed this is a isomorphism of stacks. So I think I will stop it here.
This is the easy part. You're showing that it's the stack. Now we're going to show it's an algebraic stack. Stay tuned for second half. So let's pause the recording.
Okay, so in the following, we are going to show that BG, okay, actually is an algebraic stack. So let's recall the definition of an algebraic stack from last time. So first, let's recall the definition of an algebraic space. So a sheaf on the tail side, okay, is called algebraic space. If it's satisfied the following two properties. Okay. The first, the diagonal map is representable by C. Okay. So as Justin mentioned last time, that equivalently we can characterize this condition as for any alpha spin V, the morphism, any morphism is always representable by spin. The second, there exists Excel subjective coupling. So this is the definition of algebraic space. Then we can introduce the definition of the algebraic stack. So X, let's assume that it is a stack. This is an algebraic stack. If first the diagonal, okay, is representable by the algebraic space. And we have a similar equivalent categorization. And the second, X is a smooth surjective coupling.
Sorry, I am a little confused by the equivalent. I thought it would mean that the isomorph, do you mean the groupoid itself? The isomorphisms of the groupoid are representable by? So what do you mean by the map to F is represented by a scheme?
So I mean, here you just view it as a tree.
Oh, you're saying that if I see, if I take the fiber product with any other scheme, then, okay.
Exactly.
Sorry, which would mean the isomorphisms if I take U with itself, but, okay.
Okay, any other question?
In the algebraic step, but the test of it is still affine.
Affine.
Yes.
Exactly. Okay.
So is there a distinction between smooth and orthogonal? Like they'll be different?
If it is Excel, usually it's probably one for it. So Excel is something like automorphic group will be finite. But here, if you allow smooth, I mean, automorphic group, you allow it to be not a great group. And so let's try to show that, okay, indeed, G. Okay, so indeed, we have two parts to show, okay. So usually a surjective smooth covering is called an affluent. So first, let's try to find the smooth existence of the smooth surjective covering. So actually, there's a very natural candidate. Okay. So we just consider the trivial bundle on spec K. Mapping to BG, okay, corresponding to the trivial bundle on that point. Okay. Then we claim that actually this is a desired. So to see this, or let's see, okay, so we have any test beam X. Which corresponds to some principal G bundle of X, okay. We need to compute its fiber product. And then we need to check this work. Okay, so here let's briefly recall the first time. We learned that in general, if we have two morphisms or three steps, okay, and here I1, I2. Where is a kind of metric transformation satisfying a lot of compatibilities, okay. Then their fiber product.
So,
Excuse me.
sorry to interrupt, Rachel, there was a comment from the chat. Probably the word is universal, not trivial for spec K to BG, right? Point to point mod G represents all bundles, right? All bundles get pulled back from it, not just the trivial one.
But the map here we choose is the trivial bundle, right?
It corresponds to the trivial bundle.
Yeah, it corresponds to the trivial bundle.
I see what you're
that.
saying.
Yeah.
So that answers the question. Sorry. Yeah, so map from spec K to BG will correspond to a bundle. So obviously
Yeah.
gotta be the trivial bundle.
So by definition,
Sorry.
yeah.
Sorry there, I'll write that in the chat.
Anyway. So indeed, every time we fix the map, okay, basically you just fix the bundle on that point, okay, so basically here we just choose the triple bundle here. Okay, then let's briefly recall the fiber product. Of two pre-stacks, okay. Then every time we develop S1 test scheme, okay, basically it just consists of triples, okay. 1, x2, and alpha. So x1, okay, is an object. And x2, okay. And x2 is an object. x1 is 2. And you have an isomorphism, okay. Alpha, okay. Okay, and you have a kind of, compatibilities you need to justify, okay, anyway. Okay. Now let's return to our problem here, okay. So we need to compute its fiber product, okay. Okay. So return to our situation here, okay. We want to compute the fiber product. X. We want to justify what is the group wide of any test being U, okay. And by definition, okay, I really want to draw the diagram so we need this here. Okay, so basically by definition for any test scheme, okay, you want to justify the group wide attached to the fiber product, okay. So basically it just consists of mod with alpha here, okay, and the beta here, so that the diagram is commutative, okay. So we get both alpha beta and beta such that F components of alpha that's isomorphic to beta components of trivial. And together with the isomorphism. So any questions? Basically, we just follow the definition, okay. And what is this? Okay. So alpha composed with F, we see here, it actually gives the pullback of this principal bundle to U. And what is beta composed with trivial? Okay, so the beta composed with trivial, it is still a trivial map, okay, from U to BG, okay, so we get a trivial bundle here. Any questions? Okay. But then here, okay, essentially it means that we need to fix the pullback of D along F should exactly be a trivial bundle. And any isomorphism actually is determined by a global section. Here we are.
The alpha, yeah. Like the alpha and or the extra,
But yeah, F.
There's no alpha, right?
But wait, I think you put F
This is
back.
alpha, excuse me. This is alpha. So F here determines the principal G bundle, and then you take a pullback. Yes, thank you. Any other question? So here, let me briefly make a remark that in general, a G bundle is trivial. If I'm only because the global set. It's like anyway. Okay, so essentially it means that, I mean, we want to trivialize the pullback bundle. Okay. Therefore, essentially, we will choose a section from U, okay, to this pullback. Any question? And this is exactly given by the point of P. And because let's see, by definition, okay, so we have P over what notation do I use X. So U. And here is the pullback response. And this diagram is partition in particular. Okay. And here we have identity. So every time we have a motion from U to B, okay, actually we respond to a section from U to alpha stop, okay, and vice versa. So indeed, it can be identified with PU. Okay. So in particular, we observe that actually the fiber product. I mean, what is the notation for fiber product? Valid at any test scheme of an actually it is PU. So it is represented by a scheme. Any question? Okay, therefore, I mean, the Cartesian diagram here actually here is the speed. Okay, so in particular, this map is with the subjective.
So you're assuming P is with that line?
We assume G is alpha.
Yeah.
Otherwise, the evil example of
Yeah.
concept.
Yeah. Okay, therefore we just deduce that. Okay, indeed. This is a any question? So basically, the idea is that we just look at the value of the fiber product at any test scheme, okay, and we want to try to describe that is the eventual outcome. And then you see that indeed is represented by the scheme. And similarly, we can justify the diagonal. So how much color?
All right, it's 511, so 33 by minutes, depending on.
Okay. So maybe I just skip the diagonal part. Okay. Anyway, the idea is similar. Okay. So let me briefly sketch. So I mean, the idea is similar. Okay. I mean, we fix a motion. Okay, and which corresponds to which corresponds to two principal G bundles. Okay. When we compute this fiber product, and we look at the value of each test scheme on the fiber product, okay, and it's determined by two errors alpha and beta. Okay. And then as an exercise, you can prove that indeed EG plus X evaluate at any test scheme, okay, it is actually equal to the isomorphism tree. One with the two. The morphism between these two is for G boundary. So it's an exercise. Okay, you can justify it. In particular, it has to a local trivialization. This is the G top. Okay, so in particular, indeed, diagonal is represented. Okay. Therefore, we completely prove that BG indeed is an algebraic set. So, any question? Yeah.
Just a comment for the lazy people, it's kind of a secret. 2 actually implies 1.
Yes, it's a good point. So actually, I mean, when we define the notion of algebraic space or algebraic stack, we only need the subjective itself, or maybe it's representative couple. Actually, it is in that. Thank you. Any other question?
Wait, that 2 implies 1 if we say that smooth secretly has the word representable in it.
Yes. So here we secretly assume that it's 2%.
So 1 would imply that it's representable, but you need to say representable for something like this. So
Yeah. Okay. Finally, we can introduce quotient scheme or quotient step. Okay, so every time we have a affine group scheme, okay, F on some scheme Z, okay, we can define to be the step sending test scheme U, okay, to be principal G bundle P over U. Okay, so G could vary also. And then with natural isomorphisms between them, okay. And then you can also show that this is algebraic. So you do some work, okay, and you can show that this is algebraic. So any question? Okay.
Quiz, what would the cover be? What would the chart be from X to X mod G? Oh, this is terrible class part. Yeah, there we go.
you said it right. Next one.
Yeah, exactly. Well, it's a trick question. Sorry. Right, I did. Shoot. Didn't need to get it's just.
Yeah, so Sarah said, so actually in this situation, you have a very natural afterlife. I mean, this corresponds to the trivial G bundle. And this is what is the progression. Anyway. So before proving the algebraicity of general BunG X, okay. So I would like to recall the information theory of Weil, which at least gives some motivation for me, okay, to study this kind of object. Okay. So of course, for algebraic geometry, I mean, people care about the modular properties, and it is a very natural object. But for number series like me, okay, so I mean, every time you go to a conference and the people will talk about something like BunG, and at least when I was a graduate student, I will wonder, okay, so why should I care about it? But it turns out the following way, okay, actually it is the morphic interpretation. Good part. So first we look at Weil. But here, let's assume X is a smooth projective curve of over every closed field. And here F is the function field of a third of it. And I believe that you have took the algebraic numbers in your course, and you know what you said. Yeah, okay. And A is just the restricted product. So these are close points of X.
Right there, that's a GLNO, right? A GLNO.
Yeah, yes. It's really that. Okay, so in particular, FX here is it's a completion of X. So in particular, this has nothing to do. Whereas here is okay in one variable, okay, and OX says nothing to what we call it number. Anyway,
Yeah, I guess we're assuming K is algebraically closed.
yes.
Oh, sorry, there's it is, yeah.
Here. Okay. So let's try to construct the identification. Okay, so for a number series, if we care about modular forms or automorphic forms, definitely the right hand side. It's a very natural object to study. Okay. Okay. So let's see. Okay, so by definition, the left hand side, this is the groupoid of rank n vector bundles with your X. Okay, yeah. This automorphism between them. So let's just pick up such a vector bundle, okay? And then let's, I mean, starting from this vector bundle, let's try to construct the element on the right hand side. Okay, let's see. So since we know that indeed vector bundles are locally trivial in the Zhilin topology, okay, then if we restrict to the generic point, okay, so A like here, the generic. Yeah, actually, this is a n-dimensional vector space. And similarly, if we trivialize over other points, yeah, actually, it is re-ranked by module. And over the intersection, which is puncture disk, we should have three data between them. So we need a gluing data. Here, let's tensor over F, is Fx. Here, let's tensor over OF, is Fx. And your transition, determine your transition function. So it's an element GX inside GLN. Any question? Okay, therefore from here we just get a collection of points. And we claim that actually this point lies in GLN. In other words, for almost any X, actually G lies in GLN OX. The reason is that in this trivialization, I mean, the identification is defined over, so let's be open. Therefore, for any X inside U, this transition function actually lies inside GLN OX. Okay. And finally, the identification here gives us an automorphism by GNF. Okay. And the identification here gives us the automorphism given by GNOF. Therefore, starting from any vector bundle, okay, indeed we can construct an element on the right hand side. So any question?
I just have a comment. I last time said something slightly wrong, which is I claimed that you could, any G torsor trivializes over the curve minus a point. This is false. And actually GLN is already, in line bundles, you can't necessarily trivialize over removing a point. But it is true for connected reductive G that you can always trivialize it over as risky open set by removing finite points, which is what the adels allow you to do. The finitely many sort of things that have denominators. So my conscience is now cleared.
Okay.
Sorry, when you have that eta intersect x, is that equal to x sub x? Is there something like above, or is that like a dot?
There's a dot. It means the punctuation.
Oh, okay. Wait. Oh, okay. Never mind.
Any other question? Okay. Okay, so on the other hand, conversely, from a piece of data from the right hand side, you can also construct vector bundle. But here, of course, you see that we are working with homodics rather than like a tail neighborhood. Okay, so the question is how, I mean, whether you can reconstruct the data back. Okay, then you need to use you need to use the non-trivial work of Bowen and the last law. Okay, to do the vector bundles on homodics over this.
Yeah, if you're curious about that, stay tuned for talk 6 or 7. I think it's 8. Anyway, there's going to be a talk on Weil-Laszlo and the uniformization theorems that are required to make the.
So if you want to construct that, okay, you need to use the Weil-Laszlo's formal patching. Okay, and
And also finagle it from like a QC descent, right?
yes, you're right. Also,
Because I mean, Weil-Laszlo, one thing that's non-trivial about it is they allow coefficients in like a possibly non-Noetherian.
yes.
So
Yes.
Yeah.
where you want to.
This is just the K point isomorphism.
Exactly.
Families, you
Like
have-
power series is flat.
Yes, you're absolutely right. Yeah. Finally, indeed, it is an isomorphism of group point. Okay. To make it more precise, okay. Every time we are given a process, okay. We can check that, okay, what is centralized. It turns out that the corresponding automorphism group actually is given by this is G. Yeah, and okay, this is the corresponding automorphic. This is expected. So so of course, if you follow the argument, it seems that it can be worked for more general G, and as Aaron said, you need to assume. I mean, here you need to assume that the G bundle can be trivialized over generic one. Then you need to assume, for instance, G is reductive and connected. Oh. So any question? Okay, so at least, okay, so at least right now, I mean, I'm convinced that in the bound X is important for number theory. Okay. Now let's try to prove that, okay, this is a break step.
Sorry, question. What's the grouplet structure of that?
Excuse me.
What's the grouplet structure for this?
It's a good point. So you need to look at the centralizer, and then every time you have a coset here, you check if it's centralized actually is given back. And you check that two sides. I mean the homomorphic group matches with the centralizer on the other.
Another, yeah, GLNF times GLNO does not act freely on GLNA.
Yeah.
And so you look at the things that stabilize a G.
Okay. Finally, let's try to sketch a proof for the algebraicity. So let's just try to prove that bound NF. Okay, this is algebraic. Indeed, for general G, actually can be reduced to the situation of vector bounding. Okay. So let's try to find an atlas for an next. Okay. So in particular, we need to find a smooth surjective represent for covering. Okay. For bounding X. Okay. So in some sense, it means that we need to parameterize rank n vector bundles on X, okay, by some scheme, okay. So let's briefly recall. Last time the investment talk, we have the following example. So as usual, we fix k equals k bar, okay, to get a grid close. And let's assume X is the speed. You don't need, actually, I mean, for the algebraicity of BunG, we do not need such a strong requirement, but it's fine. But with this assumption. Okay. So recall last time, I mean, we have seen that for any integer between 0 and n, okay, we have the following Grassmannian, okay, which represents the functor for alpha into x, okay, and it is achieved standing as to locally free sheaves of rank K. And here F is locally free. Okay, and here's this suggestion. Okay, then you know that indeed this is representable by a projective. Usually it is called cross-banning. And if in particular if K is equal to 1, okay, you just get the fields. So it turns out that using Sarah-Spanish's theorem, okay, actually every projective bundle can be derised as the quotient of some locally free sheaves. So in general, okay, I mean, let's see. Suppose we have a projective model, and then here let's assume U is affine, and we fix the relative and parallel line model. Okay, then say vanishing theorem. Tells us that for any coherent sheaf, X2 here exists at R0 such that for any R bigger than or equal to R0, all the higher cohomologies vanish. But you twist by M1 on n times. And UN actually is generated by global. Okay. In particular, last condition can be formulated as OXC, the structure sheet. Okay. The direct sum to the dimension of the. Here is the check. Okay. For steps to the vanishing theorem theory, you know that indeed actually any vector bundle or any coherent sheaf, okay, it can be arise as the quotient of some local free sheaf. So in particular here we can twist both sides by minus n. We just get the description. Okay. Then similar to the situation of Grassmannian, okay, in general, Grossman introduced the so-called code scheme. Which parameterize similar thing like Grassmannian. And more precisely, for any coherent sheaf on X. Let's consider the following function. So that it just sends any capacity, okay, to the corresponding positive coherent sheaves of productly presented. That is flat over U, okay. And this is ejection. Okay. And indeed, it is proved by using that indeed this is representable by a infinity union of projects. Which is stratified by the Hilbert polynomial. The Hilbert polynomial of F equalize this by n. So in particular, we look at the open subfactor, okay? Which classifies those F to be vector bundle of rank n. Okay. Actually, you can show that this is open. I mean, it is represented by open subscheme. Okay. 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 So any questions so far? Okay. And therefore, from here, I mean, indeed, we can find a atlas for our on index. So okay, so from here we know that indeed any vector bundle can be arise as the function of some, let's see, so that's the minus to some degree, okay, up to some power, okay, to some L. And moreover, you can show that by Riemann rock, okay. You can very easily show that I mean L here is just the dimension of this guy, okay. Yeah, actually this is only, I mean this is just degree, okay. Plus that's 9 times the degree over 1, okay. Plus n times 1. Anyway, okay, it only depends on the degree of the vector. Okay, so this is determined by a function depending only on n, okay. And maybe only also on the degree of the vector function. But anyway, we will get a collection of morphs of it from order x up to the outline over that. And this provides a surjective map. Okay, and moreover, you can show that indeed this map actually is C. And this is exactly the calculus. Okay, therefore, from here we just completely prove that indeed BunX is actually an algebraic set. And so the idea indeed is to use the code speed of it, this by moving, and with the help of their vanishings here. We just complete the construction of a smooth set. Any question?
The n there and there.
The n here and
Then the one n and
Yes, thank you, thank you. Let's use R, okay. Not the cost confusion. Yeah. Okay. Okay. Yeah, I think I just stopped. Yeah.
Can you say a word about why it's smooth?
Actually, you can show that this is a GR toss. You can prove, yeah, actually, you can prove that this is a GR toss.
Quad is sort of like a rigidified version of BunG, isn't it? Where you consider them as sheaves, just as
Verified of.
a version of BunG, right? You're considering the one case sheaves and the one case sheaves up to isomorphism, right?
Yes, exactly.
So it's like,
Yeah, so the point of structure here really comes from as well. Degrees is related, definitely related to our. There's something you need to work on here.
there are various nice sources if you want to go through the construction of quad, by the way. Albert's knows. We were told explicitly by Grenfell, we must not do that in this seminar. It would take too much time. Alper, if you look at chapter 2 of Alper's big notes on stacks, that is a very nice introduction. You start with to construct the Grassmannian and then go up to quote. There's another paper by Strum, I think his name is, that has a nice construction of at least of the Grassmannian, I think. But yeah.
Can you explain how the algebraicity of BunGX reduces to algebraicity of BunN?
Okay, no problem. Okay, so let's see. So okay, so the point here is that we must assume that G is actually an alpha group scheme. Okay, then we can fix the group embedding of it. From G to GIN. Okay. And this embedding provides us a natural map between stacks. Okay. So basically, here we send the G bundle to the corresponding B cross GIN. So the corresponding social bundle. Okay. Okay. Yeah, I mean. Then the point here is that this map actually is schematic. It actually is also quasi-projective. To make it more precise, okay, every time we have a bundle P here, then if you take the fiber product, what we will get here actually is this P mod G. And this can be identified as, let's see, this is E equal, yeah, N mod G, okay. So Gian has a natural action on the quotient. Then the point here is that because we assume G is alpha and in back here, actually this is the quasi-projective. Therefore, you can indeed this map actually is schematic of the quasi-projective. And from here,
So the G mod 8, the GLN mod G comes from the Chevalier theorem, right?
yes, exactly.
G mod that closes up is.
And so the point here, why is this quasi-projective really comes from the Chevalier theorem, which tells you that, I mean, every alpha algebraic group can be realized as a stabilizer of a line. Okay. 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 So here it falls function. Okay. Then from the fact that this is quasi-projective. You can show that the corresponding map. From BunG okay to down GLM. Okay, let's write down GLM. That's confusion. It's on the other hand, and the identify with the mapping stack. The G is stupid. Back. The point here is if this is quasi-projective, then this is actually schema. Which flows from 0 give us Another question?
So I feel like I remember that. I don't know if it'll come up again in the seminar, but it's definitely useful for some things that like the diagonal map for BunG is actually affine.
Okay.
It's like not clear from this, right? It's kind of interesting. I think your argument probably showed it for GLN. Because this map is actually affine. This atlas, but
you can hear.
yeah.
I see.
Like I think by the same kind of considerations from like the fact that stack axiom 2 implies 1. The atlas is actually affine. I think the diagonal is affine.
I see.
But it seems like this way of reducing to GLN probably doesn't prove it for a general.
I see. You mean the affine is the diagonal?
Yeah, and now that I think about it, yeah, I guess it's not true for a general reductive group.
Oh.
Yeah, I thought the diagonal of BunG was like really badly behaved, but
I mean, something off here is for GM, for example, it's clearly not. Well, no, sorry. No, I think it is affine. Yeah.
Okay.
Anyway, yeah.
so I guess the upshot is that you're just the actual cover, the actual atlas will be like a closed subset of this disjoint union of quads or something like that. Is that what it will look like?
It's actually open, not closed. It's open subscript.
Oh no, you take this atlas for BUN NX to get the atlas for BUN GX for general G. It'll be like a closed subset of the left hand side.
I see.
Is that what it would look like?
I'm not sure. Is it always closed? I'm not sure.
No, I did. It's just a sort of feels like you embed G in a closed way into GLN, then you should embed the cover of one in a closed way and the cover of the other, but I'm not 100% sure if that's correct.
But on the left, would you wrote like GL torser isomorphism of OX something? What is that? Something.
So actually this map is a GL torso. On each copy it is a GL torso.
But it's an isomorphism of OX.
No.
Oh,
Forget about this one.
Just GL. Okay, thank you.
Yeah, this is a GL.
Sorry, I think it's at least just sorry to go back to the question. I think it's at least clear if G is reductive that you get like if G is reductive, then GLN mod G is affine.
Yes.
Right, which I think will show this map is affine.
Yes.
So at least for reductive here. So I actually don't know if it's true for like the Borel or something. That would be interesting to think about. Like if the diagonal is affine. I don't know.
Yes, reductive should work. Yes, you're right. Yes.
Any other questions? Comments? Concerns? All right, well, let's thank this week.